So I'm Cecilia Dang, and I'm a software engineer on the AWS Lambda team. And I work on a component specifically responsible for processing streams as well as asynchronous invocations. So I'm here today to talk about real-time processing using AWS Lambda. And I'll be joined by Anders Fritz and Marco Pierleoni from Thomson Reuters, who will go over their architecture and how they use AWS Lambda and Kinesis streams to solve their real-time processing problem. So my goal for today is to dive into how going serverless with AWS Lambda can help you approach and solve a variety of real-time processing needs and problems. And by the end of the talk, I hope you walk away with a better idea of the different options you have of generating real-time events to Lambda, as well as the differences in how we process them. And because real-time really implies near real-time, and near real-time really implies some delays. There's very few things in the world that's instantaneous. So understanding the differences and how we process these events will help you better understand how your system is behaving. Specifically, I want to dive into how Lambda pulls and processes streams, as this can be one of the more involved processes, and also go into what kind of behaviors that you might expect to see when you use a stream event source, and a little bit of best practices, some metrics that you might see and want to alarm on, stuff like that. To tie things up at the end, we'll and illustrate what going real-time processing with AWS Lambda looks like in practice. We'll have Thomson Reuters coming up and talking about their architecture. So what are the different kinds of real-time event sources? We generally talk about push event sources and pull event sources. I like to think about it in these three sort of broad categories, where push event sources can also be broken down into asynchronous invoke and synchronous invoke. So push event sources is really generating the event to notify Lambda about something that just happened in real time. And how this is done is using the asynchronous invocation API or the synchronous invocation API. And I'll dive into sort of why I'm differentiating between these two in a little bit. Or you can use the pull event source model for streams. And this is really more you making this event as a reaction to a real-time action available for consumption on a stream in real time. And then it's Lambda's responsibility to then pull and process this record in response in real time. You can, a lot of these event sources, so for example, we have Amazon S3 doing asynchronous invocations, and the actions might be something like putting an item into your bucket. I don't know if you guys were at the What's New sort of talks, but we also can do gets on S3 event sources now, so that can generate events. And then S3 will notify Lambda, will notify us to do the processing. You have echoes for giving commands to an Alexa skill, and that will also notify Lambda to do some processing. If you want to have custom events, you can also directly your custom application can directly respond and throw custom events and invoke Lambda directly using the asynchronous invocation API or the synchronous one. Or you can throw it into a Kinesis stream and deliver these events and make them available for Lambda consumption that way as well. For streams, the other option is DynamoDB update streams. So that's a feature. You can turn on a DynamoDB table, and they will deliver an event. For example, if you update an item onto your table, make that event available in a stream for consumption. So the difference I want to make between the sync and async is the idea of pulling and then synchronously invoking is sort of more obvious with the streams, but really asynchronously, there's that sort of idea behind it as well. Asynchronous generally means you make work available in a queue, and then you'll have to have some work to be done to grab that from the queue and then also invoke it. And let's kind of go into more what real-time push looks like. Who does real-time push? This is any integrator that uses AWS Lambda's invoke API. So this can be S3, Amazon SNS, Amazon Alexa, who does the synchronous one, and various IoT. what it is event sources notifying Lambda for processing. And because this is more of a push notification model, the responsibility of owning this mapping is really on the event source. Lambda doesn't necessarily know who's going to notify it, but S3 knows that when you put a bucket, when you put an event or something into your bucket, they also have to notify Lambda that something just happened. Once Lambda receives the invoke, they have to do the real-time processing. And that's when we get into the differences between the synchronous and async. So for async, when you make the invoke API, you get a 202 right away. What happens in the back end is really you're telling us to queue up that work, and then you get that 202. And then in the back end, Lambda will own the processing of pulling and then synchronously invoking, making sure that function actually gets executed and processed. And compare that to the synchronous invoke, you don't really have that extra sort of work that needs to be done. When you make that invoke, right away you will be telling Lambda, start processing, and it's going to wait for processing to be done before you get a response back. And now to sort of dive into real-time pull. And you might think it's like, okay, so we're pulling events and synchronously invoking. How is this different than, like, what becomes more involved? And there's a couple factors that makes this more involved. First of all, now you're talking about pulling per shard. So you have various shards that you need to all be grabbing data from. You also have the notion where you're not deleting data when you process it. So this is a stream. So you have the concept of checkpointing and keeping track of where you are in the data, where you are in the stream. And then you also have to keep it in order. In Kinesis, there is the paradigm where the promise that you have the records in order. So let's kind of go into that in more detail. So who does real-time pull? This is Amazon Kinesis and DynamoDB streams currently. DynamoDB, and what real-time pull is, Lambda grabbing events from a stream for processing. So in this case, the mapping and the configuration itself is owned by Lambda. And when you want to configure a stream event source, you call the Lambda API create event source. And this tells Lambda that, hey, you need to start paying attention to this stream and watching it for events. So the real-time triggered events is still owned by the event source. DynamoDB is still responsible for creating this event whenever you update your table, but then they make it available for real-time processing in a stream. And similarly with Kinesis, if you have your custom application and you're creating your custom event, you put it into the stream, and then that's the end of your responsibility. Lambda then needs to grab it and then start batching up these records and invoking it in the back end. What it looks like here is when you, as a customer, when you put records into the stream, or when DynamoDB puts records in the stream, it's available across different shards, and then you have Lambda responsible for pulling it and synchronously invoking it. And this is where I'll go into, dive into more under the hood, what happens in this section, and some behaviors and observations to watch out for. Processing streams. I'll start off by going into how the different configurations impact processing and throughput at the end. So how you configure your Kinesis stream, how you configure your Lambda when you create it, and then how you actually hook them up and using the create event source API. And how different configurations on each of these components impacts the resulting processing. So with Kinesis, it's made up of shards. And the thing to sort of really note here is Lambda is going to be consuming from your stream. So it's important to know what are the limitations on the Kinesis that will impact Lambda consuming from your stream. This includes each shard supporting reading up to 2 megabytes per second, and also each shard supporting 5 control plane reads per second. So this will be across any consumers on the stream, including the Lambda event source. It's also good to note for the Kinesis side that all data is stored replayable by default for 24 hours, and this is a soft limit, which means that Lambda consumption can happen at various different points. That's why we do checkpointing, and you can also be replayable. Some sort of rules of thumbs when you're creating your stream and putting records into the stream is to make sure that the partition key distributes work evenly across your shards, because that's how consumers are going to be able to parallelize processing across your stream. And that's true for any consumers, including Lambda. And also a good rule of thumb is to pick a key with more groups than shards. This will sort of help you guarantee that you're putting good work, making them available across the shards. On the Lambda side, you have some configurations including memory. So memory not only configures the amount of RAM that's available to your Lambda function, but it also proportionally detail how much CPU, disk space, threads, and other resources available to your Lambda execution. So why is that important? Well, I mean, besides the obvious, I guess, more memory, if your Lambda function is CPU bound, generally means faster execution. And we'll go into why the function duration really impacts stream processing in a little bit. More memory can also mean you can process larger size record batches, or you can process larger records, period. If your records in your stream is variable in size, or you have variable traffic, this is when this might come into play. You also have timeout. So increasing timeout allows for longer functions. And again, the duration of your Lambda function will impact processing. One thing to watch out for is if your timeout is too long than usual, and it might take longer for you to recognize any errors that might happen. The permission model of the Lambda function includes the execution role, and it's important to note here that the execution role needs all the permissions in order to describe the stream and get records from the stream. And this is just how we are able to grab records from customer streams. When you create the actual event source between your Kinesis and Lambda function, you have a couple configurations here, including batch size. So it's important to note here, batch size is not actually the number of records that is going to be invoked in the Lambda function. It's not guaranteed to be that. So, and it's also not equivalent to how many records we grab from the Kinesis stream when we process it. The batch size is really the maximum number of records that we will invoke a Lambda function with. And I like to sort of, this is, a way I like to describe it is the effective batch size. So like what we're actually going to be throwing into your Lambda function is the minimum of records available. So that's how many records we get in a get records call from your Kinesis stream. The maximum batch size configuration that you configured, as well as any payload size limits in the synchronous invocation. And to date, that is 6 megabytes. So batch size here, when you increase it, some things you might expect to see is maybe fewer Lambda invocations when you have larger batch sizes, but each Lambda invocation is able to process more data per function. So that's really what the batch size is controlling there. You also have starting position when you configure event source. And the starting position tells us at what point in your stream are we going to start processing. The options right now include trim horizon, which tells us to start processing from the very beginning of the stream, and that's the oldest record in the stream, and then latest. So we'll start processing from the most recent record in the stream, the newest one, and it's always first in, first out, so we process on from there. If you guys were at the What's New announcement, we also now have at timestamp as a starting position, and that really allows you to be able to be particular about where you want to process in your stream. You can enable and disable your stream, pause processing your stream, and then start up again at where you actually want to start processing again. And it also allows you to be able to replay data if you need, and gives you a lot more control on where you want to start processing your data. When you configure event source, you can configure multiple functions mapped to one stream, or you can configure multiple streams to one function. So this is a many-to-many relationship, and each mapping is really a unique key pair between the Kinesis ARN and the Lambda ARN. And what this really means is that each mapping each have their own unique shard iterators. So this means that each mapping is reading from the stream all at, they can all be at different parts in time. So if you have one Lambda function that is processing slower or faster or doing other things in another Lambda function, they're not really impacting each other. They all have their different checkpointing and iterators. One thing to note though, if you have too many consumers of your stream, they're also competing for the Kinesis read limits. So that's when this comes into play. By configuring multiple event source Lambda functions to the stream, they all count as consumers. So this is kind of an example of what a record might look like when it reaches your Lambda function. You can see here it's a list of records. That's what that square bracket is. I only have one in here though. And you get information like partition key, event ID, and the data, your byte64 encoded data. Under the hood, what's happening when Lambda is processing streams is we pull. So this is pulling concurrently across the shards. You would only process, you would only have as many concurrent Lambda functions as the shards that you have in your stream. And we'll go into more on that later. If we don't get any records in a shard, we'll wait 250 milliseconds before we grab the next batch. So there's a general delay when we don't see any records. When we do see records, then we start doing the batching process and the invoking. And then it's a matter of how long your Lambda function takes. And that's when duration really comes into play. So when we grab records from Kinesis, we try to grab as much as we can. And then we keep that batch of records in memory, and then we do sub-batching to create the eventual payload that will be invoked into Lambda. So this is what I mean when you configure your batch size. It doesn't mean how much we grab from Kinesis, and it doesn't necessarily mean how much we're going to invoke your Lambda with. When we get that eventual payload that we want to invoke Lambda with, we're going to invoke it synchronously. So this is a request-response type of invocation. And we do this because we need to honor Kinesis at least once semantics. So this means we need to make sure that a batch of records was processed, or at least a best try, before we move on to the next one. And by best try, I mean until those batch of records are expired. So it essentially means that we will try our best until it's no longer possible to invoke that batch of records before moving on. So yeah, that means that each shard blocks on in-ordered synchronous invocation, and this is why your Lambda function duration really will impact your processing throughput, because really when one invocation is invoked, we're waiting for that response before invoking the next one. Here's sort of how what it looks like illustrated. Per shard, Lambda is going to call get records. I mean, this is just how processing streams works. We call it get records with the max limit. Currently, that's 10K or 10 megabytes from Kinesis, and generally not what you get back, especially if you have constant flow, in order to honor the actual read limit of Kinesis. And then if we don't get any record back, we wait a little while, and then we'll try to get records again. If we do, we keep those records in memory. We do some sub-batching logic to get the effective batch size, as I mentioned earlier. And then we do some formatting, and then invoke Lambda with the resulting payload. And then when we invoke the payload, invoke Lambda, it's going to be with a synchronous invocation. The synchronous invocation will block. So this is blocking for ordered processing. And again, this is on each individual shard, which means there is no parallel or concurrent work happening on one shard. Increasing the number of shards with even distributed work, meaning you have even work across the shards, allows for increased concurrency. And increasing or changing the batch size if it impacts duration of the Lambda function, it might take longer to process more records. And so it's important to sort of know, understand how your Lambda function reacts to more records. If it's a linear sort of relationship, it might not be as impactful to your resulting processing. Now, if your Lambda function fails, we currently retry until the records are expired or the request successfully goes through. And again, this is in order to honor the at least once semantics. What this means is if you have throttling or errors in your Lambda function, it effectively holds up processing on that particular shard. We do retry with some exponential backoff. So if there's like some service disruption, it shouldn't be that impactful. But throttles and errors are very important to monitor when you set up these Kinesis event sources. So some more little rules of thumbs I like to think about. The maximal theoretical throughput, at least as far as you know that you can get from Kinesis, is the number of shards times the maximum read limit, which is 2 megabytes per second. The effective theoretical throughput looks more like the number of shards times the effective batch size divided by how long your function actually takes, and also any retries that might happen until it successfully goes through. And it's kind of useful to sort of look at your put metrics on your Kinesis stream and compare them to your get metrics, and maybe from some estimations. If the put rate is consistently greater than ingestion throughput, you probably are going to be falling behind in processing. In that case, you might want to consider increasing the number of shards so that you can increase parallel processing, or optimizing your Lambda function and decreasing the duration. So here are some metrics that are useful here. Kinesis provides get records and also put records. So get records will kind of tell you what the effective throughput is as far as Kinesis knows, and the put records is your ingestion rate. So if your get records line is consistently higher than your put records line, you're probably falling behind in processing. Another good metric to watch out for is iterator age milliseconds, and this is a measurement of how old your last processed record was. If that number gets really high, if it's close to 24 hours, it means that the last processed record was close to expiring, and all subsequent records are probably also close to expiring. On the Lambda side, we have metrics for invocation count, duration, error count, as well as throttle count. So the error counts and throttle counts are important to monitor in this case. As I've talked about, it greatly impacts processing. And we also have logs for all these metrics as well, including the amount of memory consumed, as well as any custom logs that you have in your Lambda function. So some common observations with all these configurations and processing is the effective batch size, so how many records actually you see in a Lambda function execution might be less than what you've configured for your batch size if you have low throughput in your stream. Conversely, if you have high throughput in your stream, your batch size will likely increase. When you have increased Lambda duration, it kind of holds up processing along the whole pipeline, which means there's decreased number of invocations, as well as decreased number of get records calls. That's us grabbing records from Kinesis. So, and also, if you have too many consumers on your stream, you might start to see the metric read provision throughput exceeded, and that's provided by Kinesis. So that's another good one to alarm on. It basically tells you that you're starting to see some competition on your stream and the things that are trying to read from it and process it. So that's kind of a good overview of Lambda stream processing, and now we're going to have Anders and Marco come up.
Good afternoon, everyone. So I'm Anders.
Marco.
So we work for a company called Thomson Reuters, and for those who don't know Thomson Reuters, we are active in a couple of different industries. We're in the financial industry, we're in the legal industry, we're in the tax and accounting industry, and then the news industry. You might know the Reuters News Agency. We're going to talk about Product Insight, which is an internal tool that we developed over the last year. It's a usage, see if I get this right. It's a usage analytics solution that we developed. About a year ago, we were tasked with a challenge. We were to identify and define a solution for usage analytics tracking that enables our internal product teams to take ownership of the usage data that we track. In addition to tracking and visualizing the data, we also had to connect it to other parts of Thomson Reuters so we could augment business reference data that we keep elsewhere. It had to be safe and secure. Part of Thomson Reuters is around news, and usage of news fluctuates according to events breaking. So we had to be able to scale up as events were breaking, scale down as they were subsidizing or going down. And the other part is we are a very, very small team. So a year ago we were 4, now we're 5, 6 people. So we couldn't spend time on maintenance. We just had to maintain themselves almost. And the last part is they said, launch in 5 months. Next time, how does the solution look like?
Okay, so to reiterate, the task was to create a multi-tenant platform for the analysis of user data inside Thomson Reuters product. And this solution will have a real-time processing pipeline, but also a full data export. And it will span clients of hundreds of requests per second and clients with millions of requests per second. It will have to be more in compliance with the current vendor, and it will have to cost less than the current vendor. It will have to be easy to use by the end user, which are the product owners and the analyst. And it will have to be delivered in production in a few months. And everything will have to be implemented and managed by true developer and not working exclusively on this project. So given these premises, we knew that we wanted to leverage Amazon Web Service as much as possible. So we started thinking about it and says, which is the best tool to manage a real-time data pipeline, or data processing? And basically, our answer was to use Kinesis Stream. What we get with Kinesis Stream is basically we can just throw data at it, and what we get out of it is it's a serialized output, and basically all the events are strictly ordered inside the same shard, but also we get not destructive rate that allow us to power both parallel processing, but also give you resilience to failure. So in the way that we configure it, we have up to 7 days. In case one consumer goes down, then we can just fix the problem and resume processing or just replay it all. Plus, this Kinesis Stream scale. So if you had the need for more data, you just add more shard. So the next step was to have a master data set. So the master data set is an immutable copy of all the raw events ever ingested by your system. And we decided to use a cross-region replicated S3 bucket as storage solution for it. And the importance of having in the master data set is of a capital importance, even more for a very tiny team like ours, mostly because of replayability. So let's imagine that we just deploy something with a bug that somehow in the later processing corrupts the data. So what we can do is just deploy a fix and just replay all the data that would solve it. But also something similar would also happen if the client sends something wrong to us, which like bad data or data in a wrong format. And then at that point, we can decide to just filter out the bad data or to sanitize the data in a wrong format and just reprocess it all. Plus, so basically having in the master, what I'm trying to say is that having the master data set gives you a resilience across multiple types of failure. Plus, furthermore, if we want to introduce a new feature or a new transformation, we can apply it to both the recent data, but also the historical ones, since we have it in the master data set. We decided to use the S3 as storage solution because it's a very reliable one. It also offers you the ability to pay less for infrequent access, but most importantly, it's because it has S3 event notification, and I'm going to describe later why that's important for us. However, S3 deals with files, not events, so we need a solution that basically just batch those events into files and store them in a S3 bucket. And we are using Kinesis Firehose for that, which is a very simple tool, but also very useful. That what it does is basically what I just described. So take those events, batch in file, and ship it to S3 bucket. It also offers you compression and encryption. So the missing link here is how we take the data out of Kinesis streams and into Kinesis firewalls, and we are using a Lambda for that. We actually found in the AWS Labs GitHub account an example of it, so we just tweak it and deploy it. So let me spend a second here. So what we have now is it's a serverless architecture that is able to collect user data and to create an immutable data set. It requires very small effort to set it up, and after that point, it's completely managed by Amazon for us. The only thing that remains to do is to create a couple of alerts on CloudWatch, mostly on Kinesis and Lambda, just to be notified if something is wrong. But for the rest of it, it is completely managed by Amazon, and it is the core of our analytics solution. And since we are not managing it, we can shift our attention to other parts of the system, trying to deliver new feature. However, we cannot let the user devices to send the data directly to Kinesis stream, because in our solution, one of the requirements is that data has to be encrypted. So what we did is to add the thin layer on top of Kinesis streams, which is basically composed of ELB and NGINX collector on EC2. This is TCP load balancing, and what NGINX does after the TLS termination is to add some metadata to the event it also provision, try to authorize the request, and then just encrypt the data and ship it to Kinesis streams. So the NGINX are deployed in an auto-scaling group across two availability zones, and we're actually working right now on replicating this field layer on a second region, leveraging Route 53. So we said with Kinesis stream is able to have parallel processing. So what we did also is to attach another real-time processing pipeline. And what happens here is that basically we extract the data from Kinesis streams, we transform it and integrate it with Thomson Reuters services, and we ship it to an Elasticsearch cluster. As a side note, if we lose all the data inside the Elasticsearch, we basically can rebuild it because we have the master data set and the data inside Kinesis stream. So after once the data is in Elasticsearch, we surface it to the end user, the product owner, and the analyst through a third-party visualization tool, which is Kibana by Elastic. And at the same time we were working on this project, our internal group, our group was also working on a microservice platform, an internal one. It's named Alpha. We are using this platform for deploying and managing the more than 100 Kibana instances that we have. It also manages the authentication and authorization layer around it. We also use this platform for any other tool that we build around it, like administration console or PDF reporting. So Elasticsearch and Kibana help us covering most of the use cases we want to support. However, for a more advanced use, we also wanted to offer an alternative way to transform the data and let the user to export it so that it could be integrated in something else like Elastic MapReduce, Redshift, or AWS Athena, or anything really. So as we said before, an important feature of S3 was the S3 event notification. So once you set it up, basically what happens is that you can have a Lambda function invoked every time a new file is an S3 bucket and can potentially take the content of the file and transform it in something else. So in the way that we set it up, every time there is a new file in the master data set, as intermediate step, a Lambda function is invoked that take that file and create multiple files, one for each tenant. So at that point, we have the data set of each tenant completely separated between each other. And we can attach even more Lambda function to the specific tenant data set that allow us to have a customized transformation in case we want to deliver the data to the specific tenant in a different format. So this chain of S3 and Lambda offer you a flexible and fully managed processing pipeline, plus the fact that we are using S3 for both the intermediate stage and the final output give you multiple integration points. So for example, someone could just decide that it wants to take the master data set as it gets created and push it into an Hadoop solution, and it can just do that. So someone else could just say that he's interested in having the raw events for one project or more than one, and then would just tap in what I call here intermediate storage. So since we are also using, we are letting the user take the data directly from S3, we can use the IAM user to control the access of it. So just to finish my part, I just wanted to say that using S3 and Lambda in this function, plus all the other things that they announced this morning, I think it's very powerful, and we want to leverage way more of this in the future.
So where are we today? We launched at the end of February. We launched 2.5 months early, which was, 5 months is quick for Thomson Reuters, and actually launching in 2.5 months as opposed to 5 months was really, really quick. We have a huge adoption rate. The adoption rate is, we thought it'd be good, but the adoption rate across Thomson Reuters is a fact, what we thought times a factor of 5. Every business unit within Thomson Reuters there are product teams in every business unit across Thomson Reuters that is using it or testing it and ready to use it. What about the product itself? Since February, we had a chance of testing it in a couple of different ways. We're going to see how many events or how many requests we could test it for. We targeted testing it for 5 billion requests in a month. We're actually able to push that limit up to 4,000 requests per second, so equivalent of 10 billion events per month, and that's plenty for our purposes. Since March, and this is the good part here. Since March, we've had very, very, very little maintenance. We've had no outages. We've had no downtime. And we're using CloudWatch to monitor everything. And this part here about no outages and no maintenance is extremely important for us because we are so tiny, 5 people doing this. What has really impressed our product managers is the latency. It's from the capture of the single event to being visible in a Kibana chart. It's a few seconds, which is just superb from a usage tracking setup. We've been able to test it on the auto-scaling feature. So Reuters News, we cover news, and there's been several breaking news over the last year or so. And for the US elections, we saw a more than doubling of events captured in 24 hours compared to what we normally see on a day-to-day basis. The UK-EU referendum was almost more impressive because nobody expected the British to vote in the way that they did. So we literally went to bed at night, slept very soundly, and next morning we woke up and we thought, oh, we doubled in events overnight. And luckily we're using AWS, so we were all good, and we could come in and just check the systems and make sure that everything was okay. So here you see, the real-time chart of that EU referendum, and you could see literally track as the different districts in Britain came in, and suddenly people realized that this was not going in the way that people thought. So during that night, and so we see spikes there coming through. So the right-hand spike there is the evening of the 23rd of June into the 24th. And here you see the events that we captured during the US elections. You can see here we realized that this would be a big event, so we were able to prepare a little bit more than the EU referendum. But again, we tripled in size over in 24 hours to what we normally could do, and then afterwards we just scaled it down, and it's enormously beneficial for us because it's very, very hard to forecast news events because they just break. So having that auto-scaling, having the architecture and the tools that AWS provides is enormously beneficial, not only from a maintenance perspective, but also from a cost, and making this very, very efficient. And that's it from us. Thank you very much. Remember to complete your evaluations. On behalf of Cecilia here.